stresses on inclined areas of sections of mechanical system elements. This is Article 7.1 of the book Mechanical Systems Calculations of the Marine Facilities. Let's consider the volumetric stress strain state first, shown on the figure 7.1.1a. We can see the Cartesian coordinate system x, z, y, yeah? And we can see the balance of normal stresses acting on the selected very small piece of the material of the parallelepiped, rectangular parallelepiped located in the axis x, z, y. So to the faces of this parallelepiped applied the stresses we have sigma x along the x-axis normal stress, the and the balance sigma x equal to no, sorry, but not so much equal, but we have assumed that other stresses act as well. Yeah, but they all are in the balance. The longitudinal, the linear stress, stretching stress, normal. Sigma x acting on the face it here, on the other opposite face acts as well. The sigma y, sigma z, sigma y, and sigma z parallel to the axis. And besides, we have the per equilibrium tangential stresses tau xy, tau equal to tau yx in accordance with the law of the pairing of the tangential stresses, tau xz and tau zx as well equal due to the law of the pairing of the tangential stresses, and tau yz and tau xy applied to the this definite one, the right-angled parallelepiped, actual squared parallelepiped. On the diagram of the action of stresses on the faces of elementary loaded element of three-dimensional stress state. This is three-dimensional stress state. But a little bit more frequently, we can meet the case of the plane stress state. Plane stress state shown on the figure 7.1.1. So we have only forces. Let's assume the forces applied to the these faces perpendicular to the axis z, and the faces perpendicular to the axis y. Yeah, this stresses are in the balance as well, independent as well on the proportions of the sizes of this right-angled parallelepiped. And we do not have the stresses applied in the direction of x on the faces perpendicular to x. This is just assumed for the plane stress state. So let's consider first the plane stress state as a of the more frequently used, of the more practical needs, is more probable we can meet more probably the plane stress state of the material. So we just have to underline that the stresses within the material of the mechanical elements of the mechanical system under the external load, the stresses are not only normal stresses as well. We have sharing, and the normal we can see in other directions, to other axes of the Cartesian coordinate system. And this frequently could be the plane stress state, not instead of the more complex three-dimensional stress state. Of course, it can be as well, but for the practical needs, we could meet the issues with the plane stress state. And let's consider the plane stress state in the flat coordinate system YZ. So we assume that perhaps the stresses acting parallel the force, the axis X, are equal to 0, and all stresses are parallel only to the plane Z, Z0Y. Z0Y, the plane is of the coordinate system. So we can see. So, and the question arises: what will be in the flat stress state, in this like plane stress state? What will be if we just can change the direction of the faces of this segment of the material of the element mechanical system and the load? So, it's of the interest to find the dependence of the stresses acting on the faces of the element of the material at of an inclined side. And if we incline this side, this one, will cut by the another one plane inclined by the angle of alpha to the vertical axis y, for example. So let's consider the equilibrium of these two parts. This one part, we cut out part is well. This one part is of the element of the material from the from the mechanical body, and this is another one part. The cutout. This cutout part is a little bit more complex because consists of the 1, 2, 3, 4, 1, 2, 3, 4 faces after the cutout, and this is consists only of three. One inclined and the vertical and the horizontal parts of the element of the body. This body is of the length. Yes, let's assume very small piece of material, small. That means that it length along the abscissa axis dx, a small increment of the dz is z horizontal axis, a small differential increment of the length along axis, along the applied axis, and a very small element along the size of the element dy along the ordinate axis, and the abscissa axis is directed toward the plane, and we do not see the abscissa axis, but we assume that if we consider the plane steady state, perhaps there will be as well the element of the length along the reference axis of abscissa, as well a very small of the length dx. So let's assume that the vertical size of this physical body is dy, and the angle of inclination alpha. Dy is arbitrary, alpha is as well arbitrary, is about the same as the reference variable. So the ratio of the length dl, the length is hypotenuse, so this is a right angle triangle of the length of dl and the initial size dy. This is dy, initial size of this the element of mechanical body with the slope alpha of elementary side and the ratio of the horizontal size ds. This is horizontal size ds. Very small horizontal size ds to the size dy. So we can find that it's the proportions of dl to dy. dy is one of the legs. The adjacent leg to this, the adjacent leg to this angle alpha, the inclination of the slope, and this is the opposite leg. This is hypotenuse part of the cutout section. And we can find the proportions dl to dy equal to 1 divided by the cosine of the adjacent angle. Yes. So dl we divide by the cosine is a trigonometric function less than 1. So we have to, this is hypotenuse bigger than the leg. So we can find this by division of the cosine of the adjacent angle. And this is other ds size of the cutout part. We say ds, and ds proportion to dy. dy is assigned as a variable. We have to derive all sizes of this right angle triangle. It is not a right angle triangle. It's like a prismatic shape figure, because another one size could be dx, but we consider the plane steady state. But the other leg is ds in proportion to dy, to the first one leg adjacent to the hypotenuse by the angle alpha, can be 1 divided by tangent alpha. So yeah, we have to find one leg by the another one, and the tangent, the angle of the opposite to the first leg. Okay, so this is the figure showing the areas of the faces of this cutout part, rectangular triangle cutout part of the this is y, this is h, and we have a little one length of the cutout part equal, because we consider plane steady state could be dx by the another axis. We assume it is, but we consider only the plane steady state with not the forces in the direction of the x, forces, traces. So this is the proportions of the dl dependence on the areas, the areas of the faces. This area is ds by multiplied by dx. This area of this face on the leg and on the length of the increment of the reference axis dx, d equal to dy by dx, and dA with the index L. L means that for the hypotenuse is equal to dl by dx as well. So they all are of the length dx. And we have the stresses in the inclined area. So now issue is to find what is dependencies of stresses in the inclined area, dependence on the angle of the inclination and on the assigned stresses or the plane stress state, sigma y, sigma z, and tau. Tau we have Bismuth index because due to the law of the appearing of the tangential stresses, this tangential stress equal to this one tangential stress. So we don't need to indicate like tau z or this tau y, for example, because they are equal. So just tau. So we have the cutout part. We consider this a smaller one because of the less number of the faces of the rays complex, and another part of the segment of the material of the physical body, of the rigid physical body. Maybe not rigid, not so much important. Maybe they're just rigid physical body this way. And let's consider the conditions of the equilibrium of the indicated cutout part shown on the figure 7.1.3 B. So we have the stresses. There's normal stress on this one, right? One face is given on the leg dy, and tangential stress tau, and the normal stress sigma z. When we consider the conditions of the equilibrium, we have to consider not the stresses, but we have to consider the forces. So we have to remember that the force equal to the stress, magnitude of stress multiplied by the elementary area. Elementary area we have here one, the up one, ds by dx, this right one is dy by dx, and the left one inclined dl by ds, and the forces. Besides, we assume the auxiliary coordinate system, auxiliary u and y, Euro auxiliary coordinate system with the cutout part. We have the normal stress sigma alpha applied to the this one small side inclined, this side inclined to the engulf. So we indicate this is sigma alpha and the tau alpha. And we have tau as well because we got it from the beginning. So it is equal to tau due to the law of the pairing of the tangential stress is normal. Normal stress sigma y, and the length ds, and the area of the up one face is equal to ds by dx. So let's consider the equilibrium of this segment cutout. And equilibrium usually we consider as the equality to zero of the applied forces, so equality to zero of the applied moment. We will consider the equality to zero of the applied forces. So to find each forces acting on the faces of this cutout part of this one segment, we have to multiply the acting stresses on the increments of the area DAS for this one stresses, and DA just for this one face, and this is dl by the dx for this one stress and this. Let's consider the equilibrium of acting forces in projection on the auxiliary axis u, So to do that, first we have, besides of the finding of the areas of each of the planes, each of the sides of this element segment of the mechanical body, we will have to find the projections of the action stresses on the auxiliary axis u. So for the first stress, the force acting on the up one side sigma y and tau, we have to consider this upon the projection on the axis auxiliary axis u, considering the angle of the inclination with this face alpha. We can find the projection of the normal stress as minus multiplied by sine of the alpha of the inclination. This right angle triangle is geometrically similar to this one, but just returned to another direction, and this axis is parallel to axis u on this one scheme. So the angle alpha we have, and we have minus sigma y multiplied by sine alpha. Y minus because this directed opposite to direction of the auxiliary axis u. So we have as well that tau. Tau is tangential stress applied to the up one face of the cutout segment of the considered mechanical body, and we have the cosine of the alpha minus tau my cosine alpha. So let's feel the this tau cosine alpha, this ds, the area of the up one side of the cutout part. This is ds, the area of the cutout part, and sine alpha. This is a result of the projection of the elementary force acting on the up face of the cutout part on the auxiliary axis u. And this is sigma alpha by dl alpha. This is the projection of this subject to find the normal stress action on the inclined plane of the cutout of the segment. And this is the projections of the stresses acting on the vertical side here, vertical tau and sigma. We have to find the projection of the stresses onto the auxiliary axis u. So the projection of tau is equal to minus tau as well, minus because the opposite direction to the axis u, multiplied by sine alpha. And this is the projection of the normal stress action on the right one face of the segment of the mechanical body on the axis u by the cosine alpha. We have to find in all definitions of the projections of the angles of the inclination in the right angle triangle. So this all we do introduce in the equation to the balance of the projection of forces on the direction on the auxiliary axis u. So this is tau dA sine alpha. This is of one, and dA is the increment of the area corresponding to the right one side of the cutout part, vertical side of the cutout part. This one area is dA. And so this is minus sigma z by cosine alpha, and the area of inclination. Okay, after that, for all areas of the sides, we can introduce this area as the definite size in the considered plane. Definite size, dy, dl, ds, definite sizes, and we determine this all areas as products of this size of definite one. The size definite one faces of the cutout part of the mechanical body multiplied by 8 lengths, increment dx. So we can derive it out of the brackets, and we can divide by that because it has to equal to 0 according to the balance of the forces in equilibrium equations. After that, we have to do some transforms. So we can find this stuff. This is the same summons, but with not dx, and only dy remains. And we redefine all increments of the sizes in the plane of the consideration, all sizes ds, dy itself, and dl by the dy in accordance with the angle of inclination, the right angle triangle. This any one leg hypotenuse in the leg to dy another one leg. So using the cosine function and sine function, we can redefine the this is cut out. We divided by that due to the equilibrium not so much important, the common factor out of the brackets, and all remained parts of the areas within the brackets we redefined by the arbitrary assigned size of this axis dy. This is small but arbitrary assigned. We have defined these two, the leg and the hypotenuse by dy, and the cosines of the angles of the inclination. We did that in this one equation. And after that, we can reduce the common factor dy as well as the multiplication by common factor have not so much important as well as the dx, and only remain the stresses, and the trigonometric functions of the stresses. This is the result of transformation of the balance equation of the forces projections on the auxiliary axis u. And after that, we use the mathematical transform of trigonometric functions to multiply by sine alpha and by cosine alpha equal to sine of 2 alphas. this was substitute for the t. We can see that the tau minus tau multiplied by sine alpha. This again minus tau sine alpha. We have minus 2 taus multiplied sine alpha and cosine alpha. That's why we can 2 multiply sine alpha cosine alpha can find as a sine of 2 alphas. And this is definition of the normal stress action in the inclined cutout side of the inclined side of the cutout body, cutout of the segment of the mechanical body, segment of mechanical body. And after the same we can do for the definition of the equality of the projections of forces on the axis V and axis V, yeah. As well, here we can consider another one axis, auxiliary axis V, and we find all projections of all stresses acting in all projections of stresses on the inclined axis V, tangential axis. We can account the tau alpha projection of the axis V will be equal to tau alpha. Yeah, but we have to account as well the areas of sides. The first side areas dl and dx out of the brackets we have here. And ds sans alpha, this is upper one, the whites of the cutout part of the mechanical body, but dx we have out of the bracket. So this is the area ds by dx, etc. So we consider all stresses acting in the projections on the V, only the sigma alpha projection on the perpendicular axis we have to be equal to 0. So all other have the projections sigma y, tau, sigma z, tau is equal to great due to the law of the pairing of the tangential stresses. And after mathematic transform, we can find that we just remove the common factor because equal to 0 is dx not equal to 0. So using the formulas for double angle, the same formula as we had here, double angle, we have here double angle 2, sine alpha cosine alpha, yes, and for minus sigma y plus, we have to consider, because this sigma y, sigma z with the sine alpha cosine alpha. And after the and we consider another one mathematical transformation, cosine quadrat alpha minus sine quadrat alpha equal to cosine of 2 alphas. Sine quadrat alpha, this is cosine quadrat alpha, this is sine quadrat alpha, this is plus, this minus, but together we can consider as cosine alpha minus sine alpha. So we can find that the shear stress in a re-inclined at an angle alpha is the ratio of in the numerator sigma y minus sigma z divided by 2 multiplied sine 2 alpha, and plus tau, the tangential stress multiplied by cosine 2 alpha, the inclination of the cutout plane. Okay, and the particular case, some of normal stresses in mutually perpendicular sections and axial load when stretching element of mechanical system shown on the figure 7.1.5a, the normal stress in the cross section equal to sigma z. Here we can find sigma z is stress equal just sigma of f divided by a, and the shear stress in the perpendicular side perpendicular section to the active applied force, the shearing stress is equal to 0. Wherein the section of rod inclined by angle alpha, the normal and tangential stresses are equal. So we can use the same formulas got sigma alpha and tau alpha on the actual stretching of the material. We can find that the sigma alpha equal 0.5 sigma by cosine squared cosine alpha. This is because sigma alpha is equal to sigma by cosine alpha. It's due to the due to this formula, we have the stretched material along the axis z. Sigma y equal to 0 is just only actual stress. Sigma z only we have. So we have only the second one summoned. And tau alpha is equal to minus 0.5 multiplied by sigma. multiplied by sine to alpha. This is due to the second one, this decision. So we have only sigma z and we don't have tau. So only we have sigma z divided by 2 multiplied by 2 alpha. This is only part of this formula got. We can find what is the, when we apply it to this definite one actual stretching of the mechanical body, we can find the dependencies of the normal stresses and then tangential stresses in the inclined side of the cutout part of the this mechanical body. And if the angle of inclination of the sectional ejection load and element of the mechanical system is 45%, that is pi plus minus pi divided by 4, then the normal shear stresses in the inclined section are equal to the normal and shear stresses are equal. So if you have the side inclined by the angle of 45 degrees, the shear stress and the shear stress at alpha and sigma alpha will be equal. They will equal or 0.5 by sigma, the sigma of the normal stress in the transverse section of this segment of mechanical body, or for tau we have plus minus 0.5 by sigma. By sigma, the stress sigma z is equal to sigma because no other stress is assigned originally. So sigma z we just with not the index just consider as a sigma. And is exactly, yeah, it's very interesting to see that for the plane inclined by the angle of 45 degrees to the assigned normal stress, if we have only stretching, the in the inclined side, the tangential, the normal stresses will be equal to each other by the magnitude exactly. This is important because many materials have the critical state due to suspect of the destruction. Many material are suspect of the destruction if by the plane inclined by the angle 45 degrees. This is likely, and this is in the one of the hypotheses of the destroy of the mechanical bodies is the hypothesis of the maximal tangential stresses hypothesis used. So it's a very good hypothesis. So, and another one question arises, what is about the normal stresses in the perpendicular side. So if you here just only cut out of the mechanical body, the arbitrary segment of the mechanical body inclined to the assigned mechanical body by the angle, but the right angle, the rectangular shape of this segment we will have, and what will be dependent on the inclination of the this mechanical body cut out of this one. What will be the ratio of the stresses? Excuse me. What will be the total of the stresses acting on the segment arbitrary of the shape like this one, like squared stress, squared shape cut out, and what will be the normal stresses together, the total of the normal stresses. So what will be the equality of the sigma alpha, the normal stress in any inclined to the angle alpha, arbitrary angle alpha, just assigned angle alpha, normal stress in the plane and in the perpendicular plane, if we consider them together, alpha plus pi divided by 2. And the total of this stresses of normal stress to the plane of inclined by the angle alpha of the to the assigned stresses, originally assigned stresses in the system of coordinate x, excuse me, y 0 z. In the system of coordinate we have the any inclined, arbitrary inclined plane by the angle alpha to the axis of z, applied axis. And we have the perpendicular side inclined by alpha to this applied axis plus pi divided by 2, this perpendicular side. So we have two sides. selected in the elemental mechanical body inclined, but perpendicular to each other, by the angle pi divided by 2. So this is determination, the angle alpha sine alpha until to here. This is 1, 2, 3 summons. It's the definition of the sigma alpha, sigma y multiplied by sine squared alpha plus sigma z multiplied cosine squared alpha plus tau multiplied by sine to alphas. And this is the definition of the second summand, sigma alpha plus pi divided by 2 sigma y. The same formulas, but instead of the alpha, we substitute in the formula this one formula. We consider of 3 summands. And but as an argument of the trigonometric functions, we consider alpha plus pi divided by 2, this perpendicular side to the first side inclined by the angle alpha. So we can substitute that all. And after the mathematic transforms, when we consider the dependence of sine alpha and cosine alpha plus pi divided by 2, etc., we can find when deriving this total sigma alpha plus pi divided by 2, but these 6 summands after mathematic transform the summands with transforming trigonometric functions of alpha plus pi divided by 2 to definite trigonometric function, no cosine, but another one with just alpha argument. We can next find that we can have just only the total of sigma y plus sigma z assigned normal stresses in the directions parallel to the axis y and z. So in any segments cut out of the mechanical body, having the perpendicular sides perpendicular to each other sides, the segment of the mechanical body cut out of this mechanical body, but inclined to the axis of the coordinate system in which we have the assigned sigmas, the normal stresses, parallel to the axis y and z, but inclined by the angle alpha to stresses, but perpendicular to each other. These 2 normal stresses perpendicular to each other. We can find that independently on the angle alpha of the inclination of this segment cut out of the assigned mechanical body, independently on this angle of the inclination, the total of these 2 normal stresses actually in the perpendicular faces of the cutout part of the mechanical body, perpendicular faces, the total will be equal to the total of the assigned normal stresses. Yeah, so this is the conclusion that the sum of normal stresses in mutually perpendicular sides, sigma alpha and sigma alpha plus pi divided by 2, are equal to the total of the perpendicular stresses assigned parallel to the coordinate system axis y and z. This is constant. This remains. Okay. Questions and comments. 7.1.1, the action of mechanical stress on volume element of an elastic material in 3-dimensional stress state in the plane stress state. Scheme of the plane stress state as a possible simplification of 3-dimensional stress state, if such simplification is possible. In volume element of elastic material, the action of mechanical stresses satisfies the balance equations, because we have to consider that this element of the volume element of the elastic material is in the equilibrium. That's why we have to adopt the equilibrium. The stresses actually on the opposite faces, parallel faces, have to be equal to each other, and besides the tangential stresses have to satisfy the law of the pairing of the tangential stresses. This is due to the rules of the stability of this element. Stability in the direction of all forces, action of the element, all forces in 3-dimensional projections of the forces. And due to the stability, considering the rotating moment of this volume element of elastic material. And sometimes we can simplify this scheme and reduce the number of the stresses action on the element mechanical system if you consider the plane stress state. Plane stress state is an important characteristic issue when we decide about the stress state of the in the practical issues for the elements of the mechanical system, considering the criterion of the strengths of the elements of the mechanical system. The plane stress state is a frequent substitute of the volumetric stress state. 7.1.2 normal and shear stress is action on the inclined side, the balance condition for a part of volume element when cut out by inclined side. Finding stress projections on directions inclined to axis using the vector schemas. Yeah, we can use a vector schemas. And to find the, when we have assigned element of the mechanical system, considering the plane stress state, we can, the same as well is true for the volumetric stress state. Yeah, but simple to explain for the plane stress state. If we have assigned normal stresses parallel to two axes in the plane coordinate system and the sharing stress action on the faces of the assigned element of the mechanical system in the stress state, we can find the stresses acting in the inclined section of this element. To do that, we have to consider we have to use the sections method, and we have to consider the stability of the cutout part. We use the inclined for definite angle, inclined side, and we adopt the auxiliary coordinate system corresponding with this inclined side. And after that, we consider the equilibrium of the equality to zero of all forces acting on the cutout part in the auxiliary coordinate system. Thus, we can find the stresses acting in the inclined side. And 7.1.3 normal and tangential stresses in a platform inclined to a certain angle, taking into account the equilibrium of the part cut out from the loaded element. Yes, so we can next have the balance equations of the forces acting on the sides of the element in the plane stress state. We can next reduce the factors of the sizes of this element, as we have the very small sizes dx, dy, dz, dy, redistribute all sizes of the planes of the application of the stresses, redefined by the one or two sizes, like for example, one size could be dx of the longitudinal axis perpendicular to the plane of the flat stress state, and redefined by the one of the sizes in the plane of the coordinate system in the plane stress state. And after that, we can reduce it, and we can find the dependence of the stresses in the inclined side of the segment of the cutoff segment of the mechanical body, elastic body, and we can find it as the stresses in the inclined side and dependence just only on the angles of the inclination of the cut side of this segment of the mechanical body. 7.1.4 equal in magnitude normal tangential stresses provided the angle of the inclination of the section adjacent load of the element of the mechanical system is equal to plus minus 45. That is pi divided by 4. Plus minus pi divided by 4. If we have a good decision of dependence of the normal and tangential stresses in the inclined side, inclined for definite angle alpha, and action of the normal and normal stresses parallel to two axes in the plane stress state and the tangential stress. So when we substitute only one, the longitudinal stress, considering the stretches in the good formulas, we can find the dependencies of the normal and tangential stresses in the inclined sides in the case of the actual stretching of the mechanical body. Only stretching with not as a tangential or stresses in the assigned load to the mechanical body and the normal stresses to another direction, only actual in direction of one of the axes. And having that and having the good formulas for the plane stress state, we can adopt other stresses like the another one, normal stress and the tangential stress have to be equal to 0 for the actual stretching of the mechanical body, and we can find the resulting stresses, normal tangential for the sides of inside the mechanical body and the stretching sides inclined to definite angle for direction of the stretching of the mechanical body. The maximal tangential stress will be equal if we have inclined side to 45 degree or plus minus pi divided by 4. And in the same side inclined to 45 degrees to the direction of stretching of the assigned mechanical body, if we only stretching, no other stresses on applied, no other direction, normal stress and assigned for the mechanical body, only stretching and no tangential stresses assigned originally. Then in the side inclined to the angle 45 degrees, there will be equal in the magnitude the stretching stress and the shearing stress. In this definite one plane inclined to the direction, inclined by 45 degrees to the direction of the stretching or compression of the mechanical body, axial stretching, compression, mechanical body, axial. 7.1 without the sum of normal stresses in mutual perpendicular sections of a volume element of an elastic material which remains unchanged when the sections is rotated together at any angle, the tangential stresses in which tangential stresses are equal in magnitude according to the law of tangent stress pairing. So the sum of normal stresses, when we consider the plane stress state, and within it we consider two sides in the segment of the mechanical body, considering the plane stress state with two normal stresses usually and the shearing stress applied to the mechanical body. And when we consider the small segment inside this mechanical body, and the segment has the perpendicular faces, remains perpendicular, but this segment can be at other angles of the inclination to the assigned mechanical body, this segment. And in this segment of the mechanical body, the total of normal stresses acting in two faces perpendicular to each other in the segment ones allocated in the mechanical body assigned, the total of normal stresses applied to the faces of this allocated segment of mechanical body is equal to the total of the normal stresses applied to the original mechanical body, which in we allocate this one segment. The normal stress is total, not depends on the angle of the inclinations of the common inclination of the segment of the mechanical body allocated in it. Only under the law, under the constraint that the sides of the allocated element in the mechanical body have to be perpendicular to each other when changing the angle of the inclination in the considered stress state of this segment in the assigned mechanical body. So this is one of the conclusions of the found formulas for dependencies of the normal and tangential stresses in the sides inclined for definite angle alpha in the mechanical body. Thank you.